Welcome to the Late Lab. It's very good to have you here. Before we settle into tonight's little corner of the universe, I'd love to know where you're watching from. Maybe you're tucked away in bed, half listening in the dark. Maybe you're on a late train, watching the world slide past the window. Or maybe you're on the sofa with a blanket, a cup of something warm, and absolutely no intention of doing anything productive for the rest of the evening. Wherever you are, I hope you're comfortable, calm, and ready to let a rather strange question unfold slowly. If you enjoy these quiet journeys through science, a like and subscribe really does help. The Late Lab keep glowing away in the background, and if you're already subscribed, thank you, truly. It means a great deal, and it helps these long, gentle explorations keep finding the people who need them. Tonight, we're going to ask something that sounds almost too simple at first. Why don't atoms fall apart? After all, an atom is not a tiny solid ball. It is mostly empty space. At its centre is a small, heavy, positively charged nucleus. Around it are negatively charged electrons. And according to the older rules of physics, those electrons should lose energy, spiral inward, and crash into the nucleus almost instantly. In other words, matter itself should not be stable. Your hands, your cup of tea, your pillow, your house, your entire body, all of it should have collapsed into something very different before anyone had time to complain about it. Thankfully, atoms are a little more stubborn than that. So I'll try not to make tonight's topic so fascinating that it keeps you wide awake. But if it does, at least you'll know why the universe does not immediately fold itself into a tiny electromagnetic disaster, which, as reasons for losing sleep go, is not the worst one. So let's begin, shall we? Why atoms don't fall apart. The world feels reassuringly solid at human scale. A floor holds you up. A wall stays where it is. A glass of water keeps its shape until someone knocks it over, at which point it performs the ancient and highly inconvenient ritual of becoming everyone's problem. These things feel continuous, dependable, and almost obvious. Matter seems like the simplest thing in the world because it is always there, quietly doing its job. But beneath that calm surface, matter is not simple at all. Every familiar object is built from atoms. The wood in a table, the oxygen in the air, the iron in steel, the silicon in glass, the calcium in bone, the carbon in living tissue, the hydrogen and oxygen in water, the minerals inside rock, the metals inside planets, and the gases drifting between stars all depend on atoms that remain stable long enough to build larger structures. Ordinary matter is not ordinary because it is easy to explain. It is ordinary because the universe has been kind enough to make its deeper rules extremely reliable. An atom is not like a tiny grain of sand. It is not a little speck of material with a hard outer surface. It is a structured physical system with a very small central nucleus and surrounding arrangement of electrons. The nucleus contains positively charged protons, and in most atoms, electrically neutral neutrons as well. Around that nucleus are negatively charged electrons, arranged according to the rules of quantum physics rather than the rules of everyday motion. The scale of this arrangement is almost comically uneven. A typical atom is about 1/10 of a meter across. Its nucleus is roughly 100,000 times smaller in width than the atom as a whole. If the atom were enlarged until it was the size of a large cathedral, the nucleus would be more like a tiny object near the centre, with the electrons spread across the surrounding volume in a way that cannot be pictured as neat little planets circling on rails. Nearly all the mass would be concentrated in that central speck, while most of the atom's size would come from the electron structure around it. This is one of the first strange facts about matter. The objects around us do not feel stable, because atoms are packed like solid marbles. They feel stable because atomic and molecular structures resist being pushed through one another. The feeling of solidity is not really the feeling of tiny hard balls touching. It is the result of electromagnetic forces and quantum rules acting between the particles that make up matter. When your hand rests on a desk, the atoms in your hand and the atoms in the desk are not calmly merging into one another. Their electrons are interacting, repelling, and refusing to be squeezed into the same arrangements. The desk is, in a very real sense, saying no thank you. At the heart of the atom is the electromagnetic force. This is one of the fundamental interactions of nature, alongside gravity, the strong nuclear force, and the weak nuclear force. The electromagnetic force acts between electrically charged particles. Particles with the same kind of charge repel one another. Particles with opposite charges attract one another. Protons are positively charged. Electrons are negatively charged. So the electron is attracted toward the nucleus. The basic pattern of electric attraction and repulsion was studied carefully by Charles-Augustin de Coulomb in the 18th century. Coulomb's work helped establish that the electric force between charged objects depends on the size of the charges and the distance between them. In simple terms, stronger charges produce stronger forces, and charges closer together interact more strongly. This became known as Coulomb's law, and it remains one of the foundations of electrostatics. So, at first glance, the atom appears to have a built-in reason to hold together. The positive nucleus attracts the negative electrons. That attraction should help bind the atom, and in one sense it does. Without the electromagnetic force, atoms would not have their familiar structure. Electrons would not be drawn into atomic states around nuclei, and chemistry as we know it would not exist. But the same attraction also creates the great puzzle. If the electron is pulled toward the nucleus, why does it not simply fall in? If opposite charges attract, why is every atom not a brief little accident, ending almost as soon as it begins? This is where the word stable becomes much deeper than it first appears. The stability of atoms is the reason molecules can exist. Molecules are built when atoms bond together in particular arrangements. Water molecules depend on hydrogen, and oxygen atoms retaining their identities. Carbon dioxide depends on carbon and oxygen. Proteins, sugars, fats, minerals, salts, and the long molecules inside living cells all depend on atoms that can hold their structures, share or transfer electrons, and form lasting patterns. If atoms were constantly collapsing or rearranging without stable rules, chemistry would be impossible. Biology would never get started. Rocks, oceans, clouds, planets, and people would not have the dependable forms we recognize. Even the air seems peaceful only because atoms and molecules remain themselves for long enough to drift, collide, react, and separate in orderly ways. A breath is not a random fog of collapsing particles. It is a mixture of stable nitrogen molecules, oxygen molecules, argon atoms, carbon dioxide molecules, water vapor, and tiny traces of other gases. The calmness of breathing depends on an invisible atomic discipline. The same is true of the materials of Earth. Iron atoms can form metal because their electrons follow stable quantum rules. Silicon and oxygen can build minerals and glass. Carbon can make diamond, graphite, living tissue, and countless organic molecules because its atomic structure allows particular kinds of bonding. The richness of matter begins with the fact that atoms do not immediately destroy themselves. And this is why the question is so important. Asking why atoms do not fall apart is not a small technical curiosity. It is really asking why the material world has structure at all. It is asking why there can be chemistry, why stars can make elements, why planets can form, why living things can be assembled from molecules, and why the universe is not just a brief flash of unstable ingredients failing to become anything. For a long time, the atom was not understood in this way. The word atom originally suggested something indivisible, a basic piece of matter that could not be cut further. But as experiments improved, scientists began to discover that atoms had internal structure. They were not featureless units. They had electrons, they had nuclei, they had charges, masses, forces, and patterns. And strangely, the more scientists learned about the inside of the atom, the less obvious its stability became. What first looked like a neat explanation gradually turned into a serious problem. Once the atom was no longer imagined as a simple, indivisible object, physics had to explain how its parts remained arranged at all. The discovery of the atom's inner world did not make matter seem more secure. It made matter seem almost impossible. For a while, the easiest way to imagine an atom was to picture something like a tiny solar system. There was the nucleus at the centre carrying positive charge and almost all the mass. Around it were the electrons, much lighter, negatively charged, and somehow kept nearby by the pull of the electromagnetic force. It was a neat picture. It was simple, memorable, and visually satisfying. The nucleus became the little sun. The electrons became the little planets. The atom became a miniature cosmic arrangement, tucked inside every piece of matter. It is not hard to see why this image became so attractive. The solar system is familiar. Planets move around the sun because gravity pulls them inward, while their motion carries them sideways. They do not simply drop into the sun, because they are constantly falling around it. An orbit is, in a sense, a very graceful kind of missing. The Earth is always being pulled toward the sun, and always moving forward enough that it keeps going around instead of plunging straight in. So if a positive nucleus attracts negative electrons, perhaps electrons orbit the nucleus in the same sort of way. Perhaps the electron is pulled inward by electric attraction, while its motion keeps it circling. It sounds reasonable. It gives the mind something to hold on to. It also has the great advantage of being the sort of picture that fits nicely in a school textbook, without alarming anyone too much. Unfortunately, atoms are not tiny solar systems. The problem is that gravity and electromagnetism do not behave in exactly the same way when moving charged particles are involved. Planets can orbit the sun for billions of years without rapidly losing energy as light. But electrons have electric charge, and electric charge changes the story completely. In the 19th century, James Clerk Maxwell brought together electricity, magnetism, and light into one of the greatest achievements in physics, classical electromagnetism. Maxwell showed that changing electric and magnetic fields can travel through space as electromagnetic waves. Light itself is an electromagnetic wave. So are radio waves, microwaves, infrared radiation, ultraviolet light, X-rays, and gamma rays, though they differ in wavelength and frequency. One of the important consequences of classical electromagnetism is that an accelerating electric charge should emit electromagnetic radiation. This is not a tiny footnote. It is a central part of the classical theory. When a charged particle accelerates, it can send energy outward in the form of electromagnetic waves, and this is where the planetary atom begins to quietly fall apart. An electron moving around a nucleus would not be moving in a straight line. It would be following a curved path. Even if its speed stayed the same, its velocity would be changing, because velocity includes both speed and direction. A car going around a roundabout at a steady speed is still accelerating because its direction is constantly changing. The passengers may be moving gently, but the physics is fully aware that something is turning. An orbiting electron would have the same issue. If it were circling the nucleus like a planet, its direction would constantly change. That means it would be accelerating. And because the electron has electric charge, classical electromagnetism says it should radiate energy. That lost energy has to come from somewhere. In the classical picture, it would come from the electron's motion and position in the atom. The electron would lose orbital energy. As it lost energy, it would no longer be able to maintain the same orbit. It would move closer to the nucleus. As it moved closer, it would continue accelerating. As it continued accelerating, it would continue radiating. The process would not calmly stop at a sensible distance. Like an obedient little particle finding a parking space, it would spiral inward. The result would be atomic collapse. According to this classical reasoning, an electron should fall into the nucleus very quickly. The exact estimate depends on the model used, but the timescale is astonishingly short, far less than a millionth of a second. A hydrogen atom, the simplest atom in the universe, should not sit around patiently forming stars, water, organic chemistry, and the occasional cup of coffee. It should destroy its own structure almost immediately. This was a devastating problem. Hydrogen exists, carbon exists, oxygen exists, iron exists. The atoms in your body have not collapsed. The atoms in the room around you are not vanishing in tiny flashes of classical embarrassment. Matter clearly has stability. The world has had enough time to build stars, planets, oceans, rocks, cells, books, laboratories, and people wondering why atoms exist in the first place. So the issue was not that classical physics was off by a little bit. It was not a small correction waiting politely in the margin. It was not like discovering that a clock is running a few seconds slow. Classical electromagnetism and classical mechanics, applied directly to the atom, predicted that atoms should be unstable. They could not explain the long-lasting structure of matter, and that mattered because classical physics was not weak. It had been remarkably successful. Newton's laws described motion with extraordinary power. Maxwell's equations explained light, electricity, magnetism, and electromagnetic waves. Classical physics could describe falling objects, waves, engines, planets, lenses, circuits, and much of the visible world. It was not foolish. It was one of the great intellectual structures humanity had ever built. But the atom revealed a boundary. Inside matter, the old picture no longer worked. Electrons could not simply be treated as tiny charged planets obeying classical rules. If they were, ordinary atoms would be impossible. The very existence of stable matter was evidence that something deeper was happening. This is one of the most important things to understand about quantum physics. It was not created because scientists wanted the universe to sound mysterious. It was not invented to make particles seem strange for dramatic effect, though admittedly particles did become extremely committed to the role. Quantum physics emerged because the older rules gave answers that nature plainly refused to obey. The stability of the atom was one of those refusals. The classical atom could not survive, yet real atoms did survive. They emitted light in precise colours. They formed elements with repeatable properties. They joined into molecules. They built the material world, so physics had to change, not because curiosity wandered into an abstract puzzle, but because ordinary matter itself demanded a new explanation. The old picture of the atom was already in trouble, but it still needed one more discovery to make the problem sharper. That discovery came from Ernest Rutherford, working at the University of Manchester in the early 20th century, along with Hans Geiger and Ernest Marsden. Together they carried out one of the most famous experiments in the history of physics. It is usually called the gold foil experiment, and like many great experiments it sounds almost too simple when described from a distance. The idea was to fire alpha particles at an extremely thin sheet of gold foil and watch what happened. Alpha particles are relatively heavy, positively charged particles emitted by certain radioactive substances. At the time, they were useful little messengers from the atomic world, though perhaps not the sort of messengers you would invite to deliver a birthday card. Rutherford and his colleagues aimed these alpha particles at gold foil so thin that it was only a tiny number of atoms thick. Around the foil, they placed a screen that could detect where the alpha particles went after passing through or bouncing away. If the atom was arranged in the way many scientists expected, the alpha particles should mostly pass through with only gentle deflections, and most of them did exactly that. The majority went straight through the gold foil as if the atom was mostly open space. That part was surprising, but not completely shocking. The shock came from the few that did not. A small number of alpha particles were deflected at very large angles. Some even bounced almost straight back toward the direction they had come from. Rutherford later compared this to firing a shell at tissue paper and having it rebound. In other words, it was not the kind of result one could politely ignore while pretending everything was fine. To understand why this mattered, it helps to remember the model that came before Rutherford's nuclear atom. J. J. Thomson, who discovered the electron, had proposed what became known as the plum pudding model of the atom. In that picture, the atom was imagined as a spread-out region of positive charge, with negatively charged electrons embedded within it. The name comes from an old dessert image, with electrons sitting inside the positive material like little pieces of fruit in a pudding. It is a charming image, and also a useful reminder that even brilliant physics occasionally sounds like it wandered in from a kitchen. In Thomson's model, the positive charge was spread throughout the atom. If that were true, an incoming alpha particle would not usually meet a compact, powerful centre of positive charge. It might be nudged slightly, it might be deflected a little, but it should not often be thrown dramatically backward. Rutherford saw that the result demanded a different structure. The atom's positive charge and nearly all of its mass had to be concentrated in a tiny central region. This was the nucleus. The electrons occupied the surrounding region, while the nucleus sat at the centre, small, dense, and positively charged. This changed the atom completely. Instead of a soft, spread-out pudding of charge, the atom became mostly empty volume surrounding a compact core. Most alpha particles passed through because they did not come close to the nucleus. A few passed near enough to be strongly repelled by its positive charge, and a very small number struck the region of influence so directly that they were hurled backward. The scale is the strange part. An atom is already extremely small, roughly 1/10 billionth of a metre across. But the nucleus is smaller still, around 100,000 times narrower than the atom itself. If the full atom were expanded to the size of a sports stadium, the nucleus would be more like a tiny object near the centre, while the rest of the stadium would represent the region occupied by the electron structure. Nearly all the mass would be in that tiny central part. This makes ordinary matter feel a little unreal. The atoms that build metal, water, stone, air, and living cells are not packed with material from edge to edge. They are dominated by space and structured by forces. The nucleus is not large in the atom, but it is enormously important. It carries the positive charge that attracts electrons, and it contains almost all the atom's mass. Rutherford's model was a major step forward because it matched the scattering evidence far better than the plum pudding model. It explained why most alpha particles passed through the foil, and why a few were deflected so strongly. It revealed that atoms had a concentrated centre. It gave physics a more accurate map of matter. But it also made the stability problem worse. Before Rutherford, the atom's internal structure was uncertain enough that the collapse question could remain a little blurry. After Rutherford, the picture became clearer and more difficult. If the positive charge of the atom was concentrated in a tiny nucleus, and the negative electrons were outside it, then the attraction between them was direct and serious. The electrons seemed to be bound to a compact positive centre. The atom looked even more like a system in which negatively charged particles should be pulled inward. And if the electrons were imagined as orbiting that nucleus, the classical problem returned with full force. Orbiting electrons would be accelerating charges. Accelerating charges, according to classical electromagnetism, should radiate energy. As they radiated, they should lose energy, move closer to the nucleus, and collapse into it. Rutherford had found the nucleus, but he had not solved the atom. In fact, he had given science a sharper version of the question. The atom was no longer a vague little unit of matter. It was a tiny system with a dense positive core and surrounding electrons. It had structure. It had forces. It had an internal arrangement that experiments could probe. Yet that arrangement still should not have lasted according to the old rules. This is why the gold foil experiment is so important. It did not simply reveal that atoms have nuclei. It helped show that any successful theory of matter would have to explain how electrons remain arranged around a nucleus without collapsing into it. The discovery made the atom more real, more measurable, and more mysterious all at once. The nucleus had been found. Now physics had to explain why everything around it stayed standing. The atom now had a centre A small, dense, positively charged nucleus sat inside it, holding almost all of its mass. Around that nucleus were electrons, light, negative, and somehow arranged in a way that did not end in immediate collapse. The problem was clear enough to be uncomfortable. Classical physics said an electron moving around a nucleus should radiate energy. If it radiated energy, it should lose energy. If it lost energy, it should fall inward. Yet hydrogen atoms existed quite happily. They did not seem embarrassed by the contradiction at all. In 1913, Niels Bohr offered one of the first serious quantum answers. Bohr focused on hydrogen, the simplest atom. Hydrogen has one proton in its nucleus and one electron associated with it. That made it the cleanest possible testing ground. If physics could not explain hydrogen, then explaining carbon, oxygen, iron, or anything more complicated was going to be a rather ambitious afternoon. Bohr's idea was bold. He proposed that the electron in a hydrogen atom could not occupy just any orbit allowed by classical physics. Instead, it could exist only in certain permitted energy levels. These allowed states were not chosen by convenience or mechanical preference. They were built into the quantum structure of the atom. This was a strange move. In classical physics, a planet can orbit at many different distances from a star as long as its speed and energy match the orbit. The range is continuous. There is no cosmic rule saying Earth may orbit here, Mars may orbit there, but absolutely nobody is allowed to occupy the awkward bit in between. Classical motion is smooth in that way. Bohr suggested that electrons were different. In an atom, only certain electron energies were allowed. The electron could sit in one permitted state or another, but not halfway between them. It was as if the atom had invisible steps rather than a smooth ramp. This helped with the collapse problem, because Bohr added another remarkable rule. An electron in one of these allowed states did not radiate energy continuously. It could remain there without gradually draining itself away into light. It would emit or absorb radiation only when it jumped between allowed energy levels. That idea directly contradicted the expectations of classical electromagnetism. James Clerk Maxwell's theory said, accelerating charges should radiate electromagnetic waves. Bohr's electron looked, in some ways, like an orbiting charge, but Bohr simply declared that in the permitted orbits it did not radiate. This was not fully explained at the time. It was more like a rule placed carefully over a disaster to stop the atom from falling through the floor. But the rule worked surprisingly well. Bohr's model did not appear from nowhere. Quantum ideas had already begun to enter physics. In 1900, Max Planck had proposed that energy exchange between matter and radiation came in discrete packets, or quanta, while studying blackbody radiation. Planck was not trying to overthrow classical physics for the fun of it. He was trying to solve a very specific problem involving the spectrum of light emitted by hot objects. Then, in 1905, Albert Einstein used the idea of light quanta to explain the photoelectric effect. He argued that light could behave as if it arrived in packets of energy, later called photons. This helped explain why light of certain frequencies could knock electrons from metal surfaces, while lower frequency light could not, no matter how bright it was. By the time Bohr turned to the atom, quantization was already becoming difficult to avoid. Energy, light and matter were beginning to look less smooth than classical physics had expected. Hydrogen gave Bohr a powerful clue. When hydrogen gas is excited, it emits light at specific colours, not in a continuous rainbow. These colours correspond to precise spectral lines. Johann Balmer had found a mathematical pattern for some of hydrogen's visible spectral lines in the 19th century. Later work showed that hydrogen's spectrum contained other related series as well. Bohr's model explained these lines in a new way. If electrons could occupy only certain energy levels, then light would be emitted when an electron moved from a higher allowed level to a lower allowed level. The energy of the emitted light would match the difference between those two levels. Hydrogen's sharp, spectral lines were therefore not random decorations in the laboratory. They were evidence of the atom's internal energy structure. This was a beautiful success. Bohr's model gave the correct pattern for hydrogen's spectrum, and it offered a first quantum explanation for why the electron did not simply fall into the nucleus. The atom was not stable because classical orbits had secretly been fine all along. It was stable because the electron could occupy certain allowed states, including a lower state below which it could not fall. But Bohr's model was not the final answer. It worked best for hydrogen and hydrogen-like ions where there is only one electron to consider. More complex atoms, with several electrons interacting with one another, were much harder to explain. The model also still kept too much of the old planetary picture. It imagined electrons in definite orbits, even though later quantum mechanics would replace those paths with wave functions and orbitals. So Bohr's atom was partly right and partly wrong, which is a very respectable state for a scientific model to be in during a revolution. It rescued hydrogen, but it did not complete the theory of matter. It showed that atomic stability required quantist energy levels, but it did not yet reveal the deeper reason behind them. Bohr had not solved everything, but he had opened the door. For the first time, the atom was beginning to look survivable. The little solar system picture had helped for a while. It gave the atom a shape the mind could easily hold, a nucleus at the centre, electrons going around it. A miniature version of something familiar, reduced down to a scale far too small to see. But the more carefully physicists looked, the less that picture could be trusted. An electron is not best understood as a tiny bead travelling around the nucleus on a clear track. It does not move like a speck of dust circling a lamp. It does not have a neat little path that could be followed, frame by frame, if only the microscope were powerful enough. That image is useful for a first sketch, but it becomes misleading if we take it too literally. The real atom needed something stranger. In the early 1920s, Louis de Broglie made a proposal that changed the direction of quantum physics. If light, which had long been understood as a wave, could also behave like particles, perhaps matter, which had long been understood as particles, could also behave like waves. This was the idea of matter waves. It was a beautiful reversal. Albert Einstein had argued that light could arrive in packets of energy, later called photons. De Broglie asked whether electrons might have a wave nature as well. Not because electrons were secretly little water ripples or sound waves or anything quite so familiar, but because their behaviour might be described by a wavelength. This mattered enormously for the atom. If an electron has wave-like properties, then the allowed states inside an atom begin to look less like arbitrary rules and more like natural patterns. Instead of imagining an electron travelling along any orbit it likes, we can begin to imagine stable wave arrangements around the nucleus. Some patterns fit, others do not. A simple comparison is a vibrating string. If a string is fixed at both ends, it cannot vibrate in just any shape whatsoever. Certain standing wave patterns fit naturally along its length. The string can vibrate as one large smooth arc. It can vibrate in two sections. It can vibrate in three or more. But between those allowed patterns, other shapes do not remain stable. They interfere with themselves, cancel, or fail to form a lasting vibration. The atom is not literally a string, of course. Electrons are not plucked like tiny guitars, which is probably for the best because chemistry would become unbearably noisy. But the comparison helps. Wave behaviour can create restrictions. It can produce allowed patterns and forbidden ones. It can explain why only certain states endure. This gave Bohr's allowed energy levels a deeper physical meaning. In Bohr's model, the electron was allowed to occupy only certain orbits, but the reason was not fully clear. De Broglie's idea suggested that those permitted states might correspond to matter waves that fit around the nucleus in a stable way. If the wave did not fit properly, it could not form a lasting state. The electron was no longer just a particle being told where it was allowed to go. It was becoming a quantum object whose wave-like nature helped define what states were possible. This was not merely a poetic idea, It was tested. In the 1920s, Clinton Davison and Lester Germer carried out experiments in which electrons were scattered from a crystal of nickel. What they observed was electron diffraction. Diffraction is a wave phenomenon. It happens when waves encounter obstacles or regular structures and spread or interfere in characteristic ways. Light diffracts. Water waves diffract. Sound waves can diffract. And in the Davison-Germer experiment, electrons diffracted too. That was a remarkable confirmation of de Broglie's proposal. Electrons were not behaving only like tiny classical particles. Under the right conditions, they showed the wave-like interference patterns expected from matter waves. This discovery helped move the atom away from the old planetary picture. The electron could no longer be treated simply as a miniature object following a neat classical route. Its behaviour had to be described through quantum states, with wave-like properties built in. Inside an atom, this means the electron is not best pictured as a dot racing around the nucleus. It is better understood through a quantum state spread around the nucleus in a mathematically precise way. That state can have energy, shape, and probability structure. It can be stable, but it is not a little orbit in the ordinary sense. This is one reason atomic collapse does not happen in the classical way. The electron is not simply a charged bead accelerating around a centre and radiating itself into disaster. It occupies allowed quantum states. Those states are constrained by the wave nature of matter and by the deeper rules of quantum mechanics. The atom survives because the electron's behaviour is not free to vary continuously like a classical orbit. Only certain arrangements are physically allowed. The electron cannot choose a smooth inward spiral through every possible energy. It belongs to a quantum structure where stable states exist, and where the lowest allowed state cannot simply be bypassed on the way to collapse. So the atom becomes less like a solar system and more like a pattern. Not a mechanical toy, not a tiny clockwork system, not a nucleus with little planets obediently circling it. A stable quantum arrangement. And once that shift is made, matter begins to seem possible again. The electron had stopped looking like a tiny planet. It had become something harder to picture, but much more powerful to explain. It had wave-like behaviour. It could form stable patterns. It could not be understood properly as a little charged object tracing a clear route around the nucleus. But this raised a new question. If the electron was not following an ordinary path, then what exactly was physics supposed to describe? In the mid-1920s, Erwin Schrödinger gave quantum mechanics one of its central tools, the Schrödinger equation. The Schrödinger equation describes how something called the wavefunction behaves. The wavefunction is not a small physical cloud floating around the atom in the ordinary sense. It is a mathematical description of a quantum system. For an electron in an atom, the wavefunction allows physicists to calculate the possible states that an electron can occupy, the energy associated with those states, and the probabilities of different measurement outcomes. That last part is important. The wavefunction does not give us the electron's classical path, as if we were tracking a tiny moon around a tiny planet. It gives a structured description of what can be known, predicted, and measured about the electron. This interpretation was developed in a crucial way by Max Born. Born argued that the wave function should be understood probabilistically. More precisely, it could be used to calculate the probability of finding a quantum object in a particular place or state when a measurement is made. This was a profound shift. The electron was no longer assigned a definite little route through space in the classical sense. Instead, it was described by a probability distribution. That does not mean the electron is merely a guess, or that quantum physics is shrugging its shoulders and wandering off for a nap. The probabilities are not vague. They are mathematically precise, and they can be tested with extraordinary accuracy. Quantum mechanics does not always tell us the kind of story classical physics wanted, but it tells us a story nature appears to follow very closely indeed. This is where atomic orbitals enter the picture. An atomic orbital is not a circular road for an electron. It is not a track. It is not a little ring painted around the nucleus, with a sign saying electrons only. An orbital is a stable wave function pattern associated with an electron in an atom. It describes the regions where the electron is more or less likely to be found, along with the energy and structure of that quantum state. The simplest orbital in hydrogen is spherical. If we could represent its probability pattern visually, it would look like a soft round distribution around the nucleus, densest near the centre and fading outward. That does not mean the electron is smeared out like butter, which would be both scientifically unhelpful and rather alarming at breakfast. It means the wave function gives a probability pattern with spherical symmetry. Other orbitals are more complicated. Some have two lobes, spreading out in opposite directions. Others have clover-like shapes, with several regions of higher probability arranged around the nucleus. More complex orbitals can have layered structures, nodes, and patterns that are difficult to picture directly, but can still be described precisely by quantum mechanics. A node is a region where the probability associated with the electron is zero. In a wave pattern, nodes are natural. A vibrating string has points that remain still while other parts move. In an atom, the wave function can also have places where the probability of finding the electron vanishes. This is one more reminder that the electron state is not a tiny orbit, but a quantum pattern. These orbital shapes are connected to energy levels. Different wave function patterns correspond to different allowed energies. The electron cannot simply have any energy it likes while bound to the nucleus. It occupies one of the allowed quantum states. If it absorbs energy, it may move to a higher allowed state. If it emits energy, it may move to a lower one. But it does not drift smoothly through every possible value on the way down. This matters directly for the stability of the atom. In the classical picture, an electron moving around the nucleus should continuously radiate energy and gradually collapse inward. In the quantum picture, the electron occupies a stable state described by a wave function. When it is in one of these stationary states, it does not radiate energy in the classical continuous way. It is not following a classical curved path, so the old collapse argument does not apply in the same way. The lowest allowed state is especially important. For hydrogen, there is a ground state, the most stable state available to the electron. The electron can be bound to the proton, but it cannot keep losing energy without limit. There is no endless staircase downward into the nucleus. There is a lowest step, and quantum mechanics defines its structure. So one of the major answers to why atoms do not fall apart is this. Electrons in atoms are not unstable classical orbiters. They are described by wave functions that form stable quantum states around the nucleus. The atom is not held together by a tiny mechanical orbit that somehow avoids failure. It is held together by a deeper pattern of allowed possibilities. What looked impossible as a miniature solar system becomes stable as a quantum system. Matter survives because electrons do not behave like little planets. They behave like quantum states, and those states have shapes. There is another reason the electron cannot simply be squeezed into the nucleus, and it comes from one of the most famous ideas in quantum physics. In the late 1920s, Werner Heisenberg introduced the uncertainty principle. This principle is sometimes described as if it were only about the clumsiness of measurement, as though the problem is that scientists are trying to look at an electron with a microscope and accidentally giving it a little nudge. That image can be useful as a first hint, but it is not the deeper meaning. The uncertainty principle is not just about bad equipment. It is not a warning label attached to imperfect instruments. It is a fundamental feature of quantum mechanics. At its heart, the principle says that certain pairs of properties cannot both be exactly defined at the same time in the classical sense. The most famous pair is position and momentum. Position means where something is. Momentum describes how much motion it has, taking into account both its mass and its velocity. For an electron, quantum mechanics does not allow both of these to have perfectly sharp values at once. The more precisely an electron is localized in position, the less precisely its momentum can be defined, and the more precisely its momentum is defined, the less sharply its position can be pinned down. This is not because the electron is hiding behind a very small curtain, refusing to cooperate. It is because the electron is described by a wave function, and wave-like things do not behave like tiny classical dots. A wave that is spread out can have a fairly well-defined wavelength, but if you try to make a wave into an extremely short, sharply localized packet, you have to combine many different wavelengths together. That mixture corresponds to a wider range of possible momenta, so localization and momentum uncertainty are connected at a deep mathematical level. This matters enormously for atomic stability. Imagine trying to force the electron closer and closer to the nucleus. In ordinary classical thinking, this might seem like the lowest energy arrangement. The positive nucleus attracts the negative electron, so surely the electron should save energy by getting as close as possible. Perhaps the neatest solution would be for the electron to sit right inside the nucleus, perfectly still, having arrived at the bottom of the atomic hill. But quantum mechanics does not permit that tidy little ending. If the electron were confined into an extremely tiny region near the nucleus, its position would become very sharply defined. According to the uncertainty principle, that would make its momentum highly uncertain. In physical terms, the electron's quantum state would involve very large momentum, and therefore very large kinetic energy. So forcing the electron into a smaller space does not simply make it calmer and more settled, it makes the state more energetic. A gentle comparison is squeezing a wave into a smaller and smaller space. If a broad wave can spread comfortably, it can have a relatively smooth, low energy pattern. But if you trap it in a very tight region, the wave has to bend and vary more sharply. Those sharper variations are associated with higher energy. The electron is not a little marble being stored neatly in a tiny box. It is a quantum object, and compressing its wave function has consequences. This is why the lowest energy state of an atom is not the electron sitting motionless inside the nucleus. That classical image fails because it tries to give the electron an exact position and a state of no motion at the same time. Quantum mechanics refuses. Very politely perhaps, but absolutely. In hydrogen, the electron is attracted to the proton by the electromagnetic force. That attraction does pull the electron into a bound state, but the uncertainty principle prevents the electron from being localized into an arbitrarily small region. The stable ground state of hydrogen comes from a balance. The electron is bound by attraction to the proton, but its wave function remains spread out enough that its kinetic energy does not explode upward. The ground state is the lowest allowed energy state of the atom. It is not a collapse. It is not the electron finally giving up and falling into the center. It is a stable quantum arrangement with a definite energy and a characteristic spatial structure. This is one of the deep reasons hydrogen can exist for long periods. The electron does not spiral down through every possible orbit. It occupies allowed quantum states, and the lowest of those states is still spread around the nucleus. There is no classical crash route available. This also helps explain why atoms have size. The electron's wave function cannot be compressed without raising the energy of the state. So the atom naturally has a characteristic scale. It is not large because the electron is being held away by a tiny stick, or because the nucleus is asking nicely for personal space. It is large because quantum rules set the possible patterns of electron behavior. The uncertainty principle is sometimes presented as one of the strangest parts of physics, and it is. But here it is not just strange, it is useful. It helps keep matter from collapsing. It helps explain why the smallest stable atom has a real size, rather than shrinking into nothing. Atoms survive because the electron is not a classical object with a precise path, a precise resting place, and an unlimited range of possible energies. It is governed by quantum mechanics. Its position and momentum cannot both be nailed down perfectly. Its wave function cannot be crushed into the nucleus without becoming extremely energetic. Its lowest state is not a point, but a stable pattern. So uncertainty is not just a mist around knowledge. It is part of the architecture of matter. The atom is stable because its electron does not have an endless ladder of lower and lower places to fall. That is the quiet but powerful idea behind the ground state. In quantum mechanics, a ground state is the lowest allowed energy state of a system. It is not always the state with no energy. It is not the system turned off. It is not nature going completely still. It is simply the lowest state that the rules of quantum physics permit. The hydrogen atom gives the clearest example. Hydrogen has one proton and one electron, making it the simplest atom in the universe. The electron is attracted to the proton because opposite electric charges attract. In classical physics, that attraction seemed to create a disaster. The electron should lose energy, move inward, and keep falling until it reached the nucleus. But in quantum mechanics, the electron is not allowed to pass smoothly through every possible energy on the way down. Instead, the electron has allowed energy states. The lowest of these is the ground state. Once the electron is in that state, it cannot radiate away more energy and move to a lower ordinary atomic state. Because there is no lower allowed state available. It has reached the bottom of the quantum structure, but not the bottom in the classical sense. It has not fallen into the nucleus. It has not become motionless. It has not disappeared into a tiny point. It remains described by a wavefunction spread around the proton. This is an important distinction. The ground state is not nothingness. A quantum system in its ground state can still have structure, energy, and spatial extent. The electron in hydrogen's ground state still belongs to an orbital. It still has a probability distribution. It still has kinetic energy associated with the shape and spread of its wavefunction. It is calm only in the quantum sense, not in the everyday sense of a little object sitting perfectly still. This is why the phrase lowest energy can be misleading if we imagine it too casually. In ordinary life, the lowest energy position for a ball in a bowl is at the bottom, sitting still. But an electron is not a ball, the atom is not a bowl, and the nucleus is not a comfortable little resting place with a welcome mat. Quantum mechanics does not allow the electron to be both perfectly located in the nucleus and perfectly without motion. So the ground state of hydrogen is a stable arrangement, not a crash site. This idea belongs to the broader principle of quantist energy. When an electron is bound in an atom, it cannot have just any energy whatsoever. Only certain energy values are permitted. Between those allowed values, there are no ordinary bound electron states. The electron may occupy one allowed state or another, but it does not slide continuously through every possible value, like a dimmer switch. This also explains why atoms interact with light in specific ways. An atom can absorb light when the energy of that light matches the gap between two allowed energy states. The electron can then move from a lower state to a higher one. Later, the electron may return to a lower state and emit light, with an energy matching the difference between those levels. This is not continuous leaking. It is a transition between permitted states. That difference is crucial. In the classical collapse picture, an orbiting electron should continuously radiate energy while moving around the nucleus. It should lose energy steadily, like a tiny charged object draining itself down. In the quantum picture, an electron in a stable state does not radiate in that continuous way. Light is emitted or absorbed when the atom changes from one allowed state to another. This turns atomic stability into something measurable. When scientists observe hydrogen gas, they do not see it emitting every possible color of light. They see specific spectral lines. Each line corresponds to a particular transition between allowed energy levels. Hydrogen has its own pattern. Helium has another. Sodium, neon, mercury, calcium, and iron all have characteristic spectral fingerprints. These patterns are not decorative. They are the atom quietly revealing its internal energy structure. Spectroscopy, the study of light emitted and absorbed by matter, became one of the great testing grounds of quantum physics. In laboratories, scientists could heat gases or pass electric currents through them and examine the exact wavelengths of light produced. In astronomy, the same principles allowed scientists to identify elements in stars, nebulae, and distant galaxies. light arriving across space carried information about atomic structure. That is a remarkable thought. The stability of atoms is not only inferred from the fact that the world has not collapsed, it can be tested in the colours of glowing hydrogen, in the absorption lines of starlight, and in the precise signatures of elements across the universe. Quantum mechanics did not merely make atoms sound more interesting, it explained why atoms could remain stable, and then predicted patterns that experiments could check. The ground state is at the centre of that explanation. It says that an electron cannot keep losing energy forever. It cannot spiral endlessly downward through forbidden states. It cannot settle into the nucleus as a classical object would. The atom has a lowest allowed arrangement, and that arrangement still has shape, energy, and quantum structure. So the bottom of the atom is not collapse, it is stability. The ground state explains why a single electron in hydrogen does not fall endlessly into the nucleus. But most atoms are not hydrogen. They have more than one electron, and that creates a new question. If electrons can occupy stable quantum states, why do all the electrons in a larger atom not simply crowd into the lowest available state? At first glance, that might sound like the obvious thing to do. Systems tend to settle into lower energy arrangements. If one particular state is the lowest and most stable, then perhaps every electron should pile into it, like sleepy passengers all choosing the same warm corner of a train carriage. This would make atoms much simpler. It would also make the universe much less interesting, and possibly quite rude from a seating perspective. But electrons are not allowed to do that. The rule that prevents it is the Pauli exclusion principle, introduced by Wolfgang Pauli in the 1920s. It is one of the most important principles in all of physics, because it helps explain why atoms have structure, why the periodic table has its repeating pattern, and why ordinary matter takes up space instead of collapsing into a dense, featureless state. The Pauli exclusion principle says that no two identical fermions can occupy the same complete quantum state within a quantum system. Electrons are fermions. A fermion is a type of particle that follows a particular set of quantum rules connected to spin and identity. Other fermions include protons, neutrons, quarks, and neutrinos. Electrons all have the same mass, the same electric charge, and the same intrinsic spin size, so in a deep quantum sense, electrons are identical particles. One electron is not painted blue, and another painted green, quietly maintaining its individuality. Nature does not issue name badges to electrons, which is probably just as well. Because electrons are fermions, they obey the Pauli exclusion principle. In an atom, that means two electrons cannot share the exact same, complete set of quantum properties. They may occupy the same general shell or orbital type in certain paired ways, but their full quantum states must differ. This includes properties such as energy level, orbital form, orientation, and spin state. This principle is closely connected to Fermi-Dirac statistics, named after Enrico Fermi and Paul Dirac. Fermi-Dirac statistics describe how collections of identical fermions behave. They are not merely a convenient rule for chemistry lessons. They are part of the deep mathematical structure of quantum mechanics. The Pauli exclusion principle is sometimes taught as a rule for filling electron shells, and that is useful. But it is much more than a filing system for atoms. It is tied to the fact that electrons have half-integer spin, and are described by quantum states that behave in a particular way when identical particles are exchanged. The details become mathematical very quickly, but the consequence is clear. Identical electrons cannot all collapse into the same state. This is crucial for atomic structure. In a many electron atom, the lowest energy region cannot accept every electron. Once the available quantum states closest to the nucleus are filled, additional electrons must occupy other allowed states. They are pushed, not by an ordinary mechanical shove, but by the rules of quantum identity, into higher shells and subshells. That is how atoms acquire layers. The innermost shell can hold only a limited number of electrons. Once it is filled, later electrons must occupy states associated with the next shell. As atoms become heavier, with more protons in the nucleus and more electrons around them, the electrons arrange into a structured pattern of shells and subshells. These layers are not decorative, they determine how atoms behave. This layered structure leads directly to the periodic table. Dmitri Mendeleev arranged the elements according to repeating chemical patterns, before the full quantum explanation was known. Quantum mechanics later revealed why those patterns exist. Elements in the same column of the periodic table have similar outer electron arrangements, and those outer electrons largely determine chemical behavior. Noble gases are stable and unreactive because their outer electron shells are filled in a particularly stable way. Alkali metals are reactive because they have one outer electron that can be lost relatively easily. Halogens are reactive because they are close to filling an outer shell and readily gain or share electrons. These patterns are not arbitrary labels placed on a chart. They are consequences of quantum structure. Without Pauli's rule, the periodic table would not have its familiar architecture. Electrons would not build up in layered shells. Chemical diversity would be drastically reduced. The difference between carbon, oxygen, sodium, chlorine, and iron depends on electrons being arranged in distinct quantum states, rather than all sinking into the lowest one. This also helps explain why matter has volume. When atoms are pushed together, their electrons cannot simply all merge into the same set of states. The exclusion principle resists that compression. Along with electromagnetic repulsion, it helps give ordinary matter its size and firmness. A solid object feels solid partly because electrons are not allowed to be squeezed into identical quantum arrangements. So Pauli's principle is a major answer to why matter does not collapse. It does not merely stop electrons inside one atom from crowding into the same state. It helps create the entire architecture of ordinary matter. Atoms have shells because electrons are fermions. Elements have chemistry because atoms have shells. Matter has structure because quantum states cannot be endlessly shared. And the world around us is varied, stable, and touchable because electrons follow a rule that quietly says, "This place is already taken." The exclusion principle tells us why electrons do not all crowd into the same quantum state. But to understand how atoms get their rich internal structure, another quantum property has to be brought into view. That property is electron spin. Spin is one of those words in physics that sounds more familiar than it really is. In ordinary language, spin means rotation. A football can spin. A planet can spin. A coin can spin on a table for a surprisingly long time before falling over in a way that feels personally disappointing. But electron spin is not quite like that. An electron is not usually understood as a tiny ball literally rotating on its axis. Electron spin is an intrinsic quantum property. It belongs to the electron in the same deep way that electric charge and mass belong to it. It gives the electron a kind of built-in angular momentum, and it also connects the electron to magnetism. But it should not be pictured too literally as a little planet turning in space. The idea of electron spin was proposed in the 1920s by George Uhlenbeck and Samuel Goldschmidt. It helped explain patterns in atomic spectra that could not be fully understood with earlier models. Electrons seemed to possess an extra two-valued property, something that affected how they behaved in atoms and magnetic fields. A crucial experimental clue came from the Stern-Gerlach experiment, carried out by Otto Stern and Walter Gerlach. In that experiment, a beam of silver atoms passed through a non-uniform magnetic field and split into distinct paths rather than spreading out smoothly. The result revealed that angular momentum in atoms was quantized. Later understanding connected this kind of behavior to spin and the quantum structure of particles. Spin matters because it helps define the complete quantum state of an electron. An electron in an atom is not described only by its energy. Its state also involves other quantum properties connected to the shape of its orbital, the orientation of that orbital, and its spin. Together, these properties define which state the electron occupies. This is where the Pauli exclusion principle becomes practical. Two electrons in the same atom cannot have the same complete quantum state, but two electrons can occupy the same orbital if their spin states differ. In simple spoken terms, an orbital can often hold a pair of electrons, provided they are not identical in every quantum respect. Spin gives them that final distinguishing feature. This helps build the shells and subshells of atoms. Electron shells are broad energy levels around the nucleus. The innermost shell is closest and lowest in energy. Higher shells are generally farther out and associated with higher energies. Within these shells are subshells connected to different orbital types and shapes. Some orbitals have spherical probability patterns, others form paired lobes, clover-like shapes, or more complex distributions. These are not decorative designs. They are the allowed wavefunction patterns of electrons bound to the nucleus. As atoms grow heavier, with more protons in the nucleus and more electrons surrounding them, electrons fill available quantum states according to these rules. They occupy the lower energy states first, but they cannot all enter the same state. The exclusion principle, spin, orbital structure, and energy ordering together create the layered architecture of atoms. This architecture is the hidden reason for the periodic table. Dmitri Mendeleev arranged the elements into a table in the 19th century by recognizing repeating patterns in their chemical behavior. He did this before quantum mechanics existed, which makes his achievement even more impressive. Mendeleev could see that the elements had a rhythm. What he could not yet know was that this rhythm came from electron structure. Quantum mechanics later explained why the pattern repeats. As electron shells and subshells fill, the outermost electrons determine much of an element's chemistry. These outer electrons are called valence electrons. They influence whether an atom tends to give up electrons, gain electrons, share electrons, or avoid bonding almost entirely. Noble gases such as helium, neon, and argon are famously unreactive because their outer electron shells are filled in very stable arrangements. They are not antisocial in a personal sense, of course. They are simply quantum mechanically content, which is perhaps the purest form of not wanting to be bothered. Alkali metals such as lithium, sodium, and potassium have one outer electron beyond a filled shell. That electron can be lost relatively easily, making these elements highly reactive. Halogens such as fluorine, chlorine, and iodine are close to filling their outer shell, so they often gain or share electrons readily. This is why sodium and chlorine, two reactive elements, can form sodium chloride, ordinary table salt, through the transfer of an electron and the attraction between charged ions. The variety of chemistry comes from this layered electron structure. Carbon can form 4 strong covalent bonds because of its outer electron arrangement. Oxygen has its own bonding tendencies. Silicon, nitrogen, sulfur, phosphorus, iron, copper, and gold all behave as they do because of how their electrons are arranged in quantum states. So the stability of atoms is not merely about preventing collapse, it is about making structure possible. Once electrons are held in stable quantum states, and once those states are organized by spin, shells, subshells, and the exclusion principle, matter gains variety. Elements become distinct. Chemistry becomes possible. Molecules can form. Solids, liquids, gases, minerals, oceans, atmospheres, and living cells can exist. Atoms do not fall apart because their electrons are not wandering freely through any arrangement classical physics might allow. They are organized by quantum rules, and from those rules the periodic table quietly unfolds. Atoms do not take up space because they are tiny hard balls. That is one of the stranger truths hiding inside ordinary objects. A wooden desk, a glass window, a stone wall, and a human hand all feel as though they are made from something continuous and firm. They have edges. They resist pressure. They seem to occupy their own private region of the world, as if matter were built from little solid pieces stacked together. But atoms are not miniature stones. They do not have hard outer shells in the everyday sense. Their size comes mostly from the behavior of electrons, and electrons are described by wave functions, not by tiny surfaces. The space an atom occupies is the space over which its electron states extend, and the resistance of matter comes from electromagnetic forces and quantum rules. This means solidity is not quite what it feels like. When two atoms are brought close together, their outer electron structures begin to interact. Electrons carry negative electric charge, and like charges repel. So the electrons associated with one atom repel the electrons associated with another. This repulsion is part of the electromagnetic force, the same fundamental interaction that attracts electrons to nuclei and helps hold atoms together in the first place. There is a lovely tension in that. The electromagnetic force helps build the atom by attracting negative electrons toward positive nuclei, but it also helps keep atoms apart when their electron clouds push against one another. The same force that allows matter to form also helps stop matter from simply blending into itself. This is why two ordinary objects do not pass through each other. Their atoms are not touching like little billiard balls with painted surfaces. Instead, their electron wave functions and electric fields interact. As atoms get too close, the energy of the combined system rises. The arrangement becomes less favourable. The atoms resist being pushed into the same space. The Pauli exclusion principle deepens this resistance. Electrons are fermions, and identical fermions cannot occupy the same complete quantum state. When atoms are squeezed together, their electrons cannot all be packed into one shared set of low-energy states. Some electrons are forced into different, often higher energy arrangements. That costs energy, and it creates pressure against compression. So the solidity of matter has two closely connected ingredients. There is electromagnetic repulsion between negatively charged electron structures, and there is quantum resistance from the fact that electrons cannot all be placed into identical states. Together, they help give matter its volume. A simple example is a hand resting on a table. It feels as if the hand is in direct contact with the table, and in everyday language that is perfectly fine. But on the atomic scale, the situation is subtler. The atoms in the skin of the hand and the atoms in the surface of the table are not merging into one another. Their outer electrons are interacting through the electromagnetic force. Quantum rules prevent those electrons from being squeezed freely into the same states. The table pushes back because the combined atomic arrangement resists compression. So the support you feel is not the result of tiny solid surfaces calmly pressing together like microscopic bricks. It is the result of fields, charges, wave functions, and exclusion. The table holds up the hand because the atoms in both objects refuse, very politely but very firmly, to occupy the same quantum arrangements. This is also why ordinary matter can feel solid, even though atoms are mostly empty volume. The emptiness is not a free invitation for everything to pass through everything else. Atomic space is structured by electron states and forces. The electron region around an atom is not empty in the everyday sense. It is where the atom's electromagnetic and quantum behaviour becomes important. Of course, matter can be compressed. Air can be squeezed into a tank. A sponge can be pressed smaller. Metals can deform under enough force. Rocks deep inside planets can be compressed by immense pressure. Under extreme astrophysical conditions, matter can be crushed into forms far beyond everyday experience. In a white dwarf star, atoms are stripped and compressed until electron degeneracy pressure becomes essential. In a neutron star, matter is squeezed so violently that ordinary atoms no longer remain intact, and protons and electrons can combine into neutrons under extreme conditions. These are not gentle situations. They require pressures vastly beyond anything found on a kitchen table, which is probably for the best, as kitchen tables already have enough responsibilities. Under normal conditions, the forces available in daily life are nowhere near strong enough to overcome atomic structure. A hand cannot pass through a desk because the electron arrangements in both are stable against that kind of compression. A wall keeps its shape because atoms and molecules are locked into arrangements governed by electromagnetic bonding and quantum restrictions. A glass of water can flow because its molecules move around one another, but the molecules themselves retain structure because their atoms remain stable. So atoms do not merely avoid falling apart internally, they also help prevent matter from collapsing into itself collectively. Each atom has a structure defined by electron wave functions around a nucleus. When many atoms gather together, those structures interact. They bond, repel, arrange, vibrate, and resist compression. The same quantum rules that stop electrons from crashing into nuclei also help explain why matter has size, firmness, texture, and form. The world feels solid because atoms are stable, and atoms take up space because quantum mechanics gives their electrons a structure that cannot simply be flattened away. Once atoms are stable, they can begin to do something even more interesting. They can join together. An individual atom is already a remarkable achievement. It is a stable quantum arrangement of nucleus and electrons, held together by electromagnetic attraction, structured by wave functions, shaped by energy levels, and organized by rules like the Pauli exclusion principle. But the world around us is not made mostly from isolated atoms floating alone. It is made from atoms connected into larger structures. Those connections are chemical bonds. Chemical bonding begins with atomic stability. If atoms could not keep their own electron structures, they could not form reliable bonds with other atoms. There would be no water molecules, no carbon dioxide, no minerals, no proteins, no deoxyribonucleic acid, no crystals, no oceans, and no living cells. Chemistry depends on the fact that atoms remain themselves while still being able to interact. One of the key early figures in understanding chemical bonding was Gilbert N. Lewis. He introduced ideas about valence electrons, the electrons in the outer part of an atom that are most involved in bonding. Lewis helped show that atoms often bond in ways that give them more stable outer electron arrangements. His dot structures, where outer electrons are represented around chemical symbols, became a simple and lasting way to think about bonding. Linus Pauling later helped bring quantum mechanics more deeply into chemistry. Pauling's work on the nature of the chemical bond connected atomic structure, electron sharing, molecular shape, and quantum theory. He showed that chemical bonds were not just useful labels for how atoms stick together. They were physical arrangements rooted in electron behavior. One familiar kind of bonding is ionic bonding. In ionic bonding, one atom transfers one or more electrons to another atom. This creates charged particles called ions. If an atom loses an electron, it becomes positively charged. If an atom gains an electron, it becomes negatively charged. Opposite charges attract, so the positive and negative ions can hold together through the electromagnetic force. Sodium chloride, ordinary table salt, is the classic example. A sodium atom can lose its outer electron relatively easily. A chlorine atom can gain an electron to complete a stable outer arrangement. When this happens, sodium becomes a positively charged sodium ion, and chlorine becomes a negatively charged chloride ion. The attraction between these ions helps build the crystal structure of salt. This is not a tiny mechanical clasp. There are no little hooks clicking into place. Ionic bonding is an electromagnetic arrangement between charged particles, shaped by the energy advantages of the electron transfer and by the collective structure of many ions in a crystal. Another major kind of bonding is covalent bonding. In covalent bonding, atoms share electrons. But sharing, in quantum mechanics, does not mean two atoms are passing a little electron back and forth like a borrowed pen. A covalent bond involves shared electron states. The electrons belong to a quantum arrangement that extends across more than one atomic nucleus. This is where molecular orbitals become important. An atomic orbital describes a wave function pattern associated with an electron in a single atom. A molecular orbital describes a wave function pattern spread across a molecule. In a molecule such as hydrogen, the electron state can extend over both nuclei, helping hold the atoms together in a stable arrangement. The bond forms because the combined quantum state can have lower energy than the separated atoms. The electrons and nuclei arrange in a way that balances attraction, repulsion, wavefunction structure, and the Pauli exclusion principle. The result is a molecule with a particular shape and energy. Water is a beautiful example. A water molecule contains 2 hydrogen atoms bonded to 1 oxygen atom. Its shape is bent rather than straight, because of the arrangement of electron pairs around the oxygen atom. That shape helps give water many of its unusual properties, including its polarity, its ability to dissolve many substances, and its role in life. Carbon dioxide has a different structure. It contains 1 carbon atom bonded to 2 oxygen atoms in a straight arrangement. Proteins involve long chains of atoms folded into specific shapes. Deoxyribonucleic acid stores genetic information in a molecular structure built from stable chemical bonds. Minerals form repeating arrangements of atoms and ions. Metals, salts, sugars, fats, and gases all depend on atoms linking together in reliable ways. The stability of molecules is not accidental. Molecules have particular energies and shapes because their electrons occupy allowed quantum states. Some arrangements are stable, others are not. Some bonds are strong, others are weaker. Some molecules are reactive, ready to rearrange under the right conditions. Others are impressively content to remain as they are, rather like noble gases at a party they did not especially want to attend. This is why the question of atomic stability reaches far beyond the atom itself. Atoms not falling apart is only the first layer. The same principles that stabilize atoms also allow them to build larger structures. Quantist energy, electron wave functions, electromagnetic attraction and repulsion, valence electrons, molecular orbitals, and the Pauli exclusion principle all help explain why chemistry has order. A molecule is not just a pile of atoms, it is a stable quantum structure formed from atoms whose electrons can arrange themselves across more than 1 nucleus. Those arrangements create the substances of the world: water, air, stone, glass, salt, wood, blood, bone, and the long molecules that carry life's instructions. Matter becomes rich because atoms are stable enough to combine, and chemistry begins because atoms do not fall apart. So far, the atom has looked mostly like a story about electrons. Electrons explain the size of atoms. Electrons create shells, orbitals, and chemical behavior. Electrons help matter resist compression. Electrons allow atoms to bond into molecules. It would be tempting to think that once the electron problem is solved, the whole atom is safe. But the nucleus has its own problem. At the center of every atom, except the simplest form of hydrogen, there is a nucleus made from protons and neutrons. Protons carry positive electric charge. Neutrons carry no electric charge. Together, protons and neutrons are called nucleons because they are the particles that make up the atomic nucleus. The first difficulty is obvious once the charges are noticed. Protons repel other protons. They all have the same positive charge, and the electromagnetic force pushes like charges apart. In an atom such as helium, carbon, oxygen, iron, or uranium, the nucleus contains more than 1 proton, so the nucleus contains particles that should be electrically pushing away from one another. This creates a second stability puzzle inside the atom. The electrons are attracted to the nucleus, and quantum mechanics explains why they do not collapse into it. But inside the nucleus, the protons are repelling one another. Why does the nucleus not simply fly apart? The answer is the strong nuclear force. The strong nuclear force is one of the fundamental interactions of nature. It binds protons and neutrons together at extremely short distances. Over the scale of the nucleus, it is far stronger than the electromagnetic repulsion between protons, but it has a very limited range. It acts powerfully only when nucleons are extremely close together, over distances comparable to the size of an atomic nucleus. This short range is crucial. The strong force is not like gravity, stretching across planets and stars. It is not like electromagnetism, which can reach across large distances, though weakening with distance. The strong nuclear force is more like an incredibly powerful neighbour who only helps if you're standing almost directly beside them. Useful, but not exactly sociable. The discovery of the neutron helped make nuclear structure much clearer. James Chadwick discovered the neutron in 1932. Before that, scientists knew the nucleus carried positive charge and most of the atom's mass, but its internal composition was difficult to understand. The neutron explained how nuclei could contain additional mass without adding more positive charge. Neutrons play an important role in stabilizing many nuclei. Because they do not carry electric charge, they do not add extra electromagnetic repulsion, but they do participate in the strong nuclear force. In that sense, neutrons help add strong force binding without making the proton repulsion worse. For light nuclei, the number of protons and neutrons is often roughly similar. Carbon-12, for example, has 6 protons and 6 neutrons. Oxygen-16 has 8 protons and 8 neutrons. But for heavier nuclei, more neutrons are usually needed to help stabilize the nucleus against the increasing electrical repulsion among many protons. Lead, for example, has many more neutrons than protons in its most stable forms. Even so, there is a limit. Too few neutrons can make a nucleus unstable, because there may not be enough strong force binding to balance proton repulsion. Too many neutrons can also make a nucleus unstable, because the balance of nuclear energy becomes unfavorable. The nucleus is not stable simply because neutrons are present. It is stable only when the combination of protons, neutrons, forces, and quantum states creates a lower energy arrangement. This is where nuclear binding energy becomes important. Nuclear binding energy is the energy associated with holding a nucleus together. A stable nucleus has less total energy than the same protons and neutrons separated apart. In simple terms, the bound nucleus is energetically favored. Energy would have to be added to pull it apart into its individual nucleons. This is one of the deeper meanings of stability in physics. A stable system is not merely something that happens to last. It is an arrangement with an energy structure that resists change. The particles are not casually sitting together because nobody has suggested otherwise. They are bound into a configuration that is lower in energy than many possible alternatives. Hideki Yukawa made an important early contribution to understanding nuclear forces in the 1930s. He proposed that the force between nucleons could be explained through the exchange of a particle, later associated with mesons. His work helped open the path toward modern theories of nuclear interaction, even though today the deepest explanation is connected to the strong interaction between quarks and gluons described by quantum chromodynamics. For the story of why atoms do not fall apart, the key point is this: the atom depends on 2 layers of stability. The electrons must form stable quantum states around the nucleus, rather than collapsing inward. And the nucleus itself must remain bound together, despite the electric repulsion between its protons. Atomic stability is therefore not only an electron story, it is also a nuclear story. Matter survives because electrons obey quantum rules, but matter also survives because nuclei do. So far, atomic stability has seemed almost reassuring. Electrons occupy stable quantum states. Nuclei are held together by the strong nuclear force. Matter has structure, chemistry has order, and the universe has not collapsed into a tragic little footnote. But there is a quiet complication. Not every atom is stable forever. Some atomic nuclei are radioactive. This means they can spontaneously transform into different nuclei over time, releasing particles or energy in the process. The electrons around the atom may be arranged perfectly well, and the atom may take part in chemistry quite normally, but deep inside the nucleus, the balance of protons, neutrons, forces, and energy may not be stable. Radioactivity was discovered at the end of the 19th century. Henri Becquerel found that uranium salts emitted penetrating radiation without needing sunlight to trigger it. Soon after, Marie Curie and Pierre Curie studied radioactive materials in extraordinary detail, discovering new elements such as polonium and radium. Their work revealed that atoms were not always permanent little building blocks. Some could change from within. That was a profound discovery. In ordinary chemistry, atoms rearrange. They bond, separate, share electrons, transfer electrons, and form new molecules. But the identity of the atomic nucleus usually stays the same. Oxygen in water is still oxygen. Carbon in carbon dioxide is still carbon. Sodium and chlorine in salt are still sodium and chlorine, even though they are present as ions. Radioactivity is different. Radioactive decay involves the nucleus itself changing. In alpha decay, an unstable nucleus emits an alpha particle. An alpha particle contains 2 protons and 2 neutrons, the same basic structure as the nucleus of helium. When a nucleus emits an alpha particle, it becomes a different element, because the number of protons is changed. In beta decay, a neutron can transform into a proton while emitting an electron and an antineutrino, or in another form, a proton can transform into a neutron while related particles are emitted. The details involve the weak nuclear force, another fundamental interaction of nature. The key point is that beta decay also changes the composition of the nucleus. Gamma radiation is different again. In gamma emission, the nucleus releases energy as a high-energy photon. The nucleus may remain the same element, but it moves from a higher energy state to a lower energy state. It is nuclear transition, not an ordinary electron transition. These processes show that nuclear stability has its own rules. A radioactive atom does not fall apart because its electrons forgot how orbitals work. It changes because its nucleus has an unstable arrangement. The timing of radioactive decay is described by half-life. A half-life is the time it takes for half of a sample of radioactive nuclei to decay. If a sample contains a large number of identical radioactive nuclei, then after one half-life, roughly half will have transformed. After another half-life, roughly half of the remaining nuclei will have transformed, and so on. This does not mean each individual atom has a tiny countdown clock inside it, ticking with theatrical suspense. Quantum decay is probabilistic. For a single unstable nucleus, physics gives a probability of decay over time, not a precise appointment in the diary. But for a large sample, the pattern becomes very predictable. Half-lives vary enormously. Some radioactive nuclei decay in fractions of a second. Others persist for thousands, millions, or even billions of years. Uranium-238 has a very long half-life, while many artificial or highly unstable isotopes decay almost immediately. This range tells us that instability is not one simple condition. It depends on the detailed energy structure of the nucleus. This is important for the main question, because radioactive decay does not mean atoms in general are fragile. Many atoms are extremely stable. Ordinary hydrogen, carbon, nitrogen, oxygen, and iron can remain unchanged for immense stretches of time under normal conditions. Carbon-12, nitrogen-14, oxygen-16, and iron. 56 are examples of nuclei with stable arrangements. They do not need to decay into something else to reach a lower energy configuration. Other nuclei, however, are energetically unsettled. They may have too many neutrons, too few neutrons, too many protons, or an arrangement that can reach a lower energy state by transforming. Radioactive decay is nature moving from an unstable nuclear configuration toward a more stable one. So the answer to why atoms do not fall apart has to be careful. Many atoms do not fall apart because their electrons occupy stable, allowed quantum states, and their nuclei are bound in stable arrangements by the strong nuclear force. But some atoms do transform because their nuclei are not stable. They may emit alpha particles, undergo beta decay, or release gamma radiation. They do not collapse in the classical way imagined for electrons, but they can change through nuclear processes. This makes the truth more nuanced and also more interesting. Atoms are not eternal by default. They are stable when their quantum structure allows stability. For many elements and isotopes, that stability can last across the age of planets and stars. For others, the nucleus eventually rearranges itself into something more favorable. Matter survives not because every atom is frozen forever, but because nature provides stable states for many atoms to occupy. And when those states are not stable, the atom does not simply fall apart, it transforms. The atom began as a question about particles, a nucleus, electrons, attraction, stability. Then the story became a question about waves, orbitals, uncertainty, spin, and allowed states. But modern physics goes even deeper. Today, the most precise description of the electromagnetic interaction is not just ordinary quantum mechanics, it is quantum electrodynamics. Quantum electrodynamics is the quantum field theory of electromagnetism. It describes how charged particles, such as electrons, interact with light, and how light itself behaves in the quantum world. It is often shortened to 3 letters in textbooks, but spoken plainly, it is the theory of electrons, photons, electric charge, and electromagnetic interaction treated through quantum fields. In this modern view, electrons and photons are not understood only as tiny classical objects. An electron is associated with an electron field. A photon is associated with the electromagnetic field. Particles can be thought of as excitations of these fields, and interactions happen through the rules of quantum field theory. This does not mean the older language of particles becomes useless. It means the deeper description is more subtle. Quantum electrodynamics was developed in the 20th century by several major figures, including Richard Feynman, Julian Schwinger, Shinichiro Tomonaga, and Freeman Dyson. Feynman introduced his famous diagrams as a way of organizing calculations, showing interactions between particles as clean little pictures of lines and vertices. They look almost friendly, until one remembers that each line is quietly carrying a small library of mathematics behind it. The power of quantum electrodynamics is not just that it sounds impressive, it works with extraordinary precision. In ordinary quantum mechanics, the hydrogen atom can be described using the Schrödinger equation, and this gives the main pattern of its energy levels. But when physicists measured hydrogen more carefully, they found tiny differences that required a deeper explanation. These small shifts were not failures of quantum mechanics. They were signs that the electromagnetic field itself had quantum behavior that needed to be included. One famous example is the Lamb shift, named after Willis Lamb. In the 1940s, Lamb and his colleague Robert Rutherford measured a tiny difference between energy levels in hydrogen that earlier theory predicted should have been the same. The difference was small, but it was real. Quantum electrodynamics explained it by accounting for the way the electron interacts with the fluctuating quantum electromagnetic field around it. This is a very delicate idea. Even in what seems like empty space, quantum fields are not simply absent. The electron in hydrogen is affected by subtle field interactions. These effects slightly shift the energy levels of the atom. The atom is still stable, but its stability is not merely a rough sketch. It has fine structure, hyperfine structure, radiative corrections, and tiny measurable details. Another remarkable success is the anomalous magnetic moment of the electron. The electron behaves as though it has a tiny magnetic character connected to its spin. Quantum electrodynamics predicts a very small correction to that magnetic behavior. Experiments have measured it with astonishing accuracy, and the agreement between theory and observation is among the most precise in all of science. This matters for the question of atomic stability, because it shows that the modern atom is not held together by a vague quantum idea. It is part of a mathematical framework that has been tested again and again. The electron's behavior in atoms, the emission and absorption of light, the tiny differences between energy levels, and the magnetic properties of electrons all fit into a broader theory of charged particles and photons. The simple answer to why atoms do not fall apart is that electrons occupy stable quantum states around nuclei, and those states do not behave like classical orbits. But quantum electrodynamics refines that answer. It shows that those states are part of a deeper field picture, where electrons, photons, and electromagnetic interactions are described with extraordinary care. This does not make the atom less real. It makes it more remarkable. The stable atom on which chemistry depends is not a crude approximation that barely gets away with existing. It is a structure whose details can be predicted to many decimal places. Hydrogen, the simplest atom, becomes not just a tiny piece of matter, but a testing ground for some of the most precise physics humans have ever developed. So atomic stability is not a lucky accident. It is not a temporary loophole in the old classical rules. It is woven into quantum mechanics, refined by quantum field theory, and confirmed by precision experiments. The atom survives in the everyday world because its deeper rules are exact enough to hold. And modern physics can hear those rules in the smallest shift of light. The rules that keep atoms stable do not stay politely inside atoms. They reach outward into gas clouds, planets, stars, and some of the strangest objects in the universe. The same quantum principles that stop electrons from collapsing into nuclei also help determine how matter behaves when it is spread thinly through space, crushed inside stars, or compressed by gravity into extreme forms. A cloud of gas in space may look simple from a distance. It may seem like a faint mist between stars. But that gas is made from atoms, ions, molecules, electrons, and nuclei, all obeying the rules of atomic and quantum physics. Its temperature, pressure, light emission, and chemistry depend on the stability and structure of the particles inside it. Stars depend on this structure too. A star is not just a glowing ball of fire, although that is a very understandable first impression. A star is an enormous self-gravitating sphere of plasma, where gravity pulls matter inward while pressure pushes outward. In ordinary stars like the Sun, that pressure comes mainly from the motion of particles in hot gas and from radiation produced in the core. Atomic nuclei, electrons and photons move, collide, scatter, and carry energy through the star. The Sun remains stable over long periods because gravity and pressure reach a kind of balance. Gravity tries to compress the star. Thermal pressure, supported by the motion of particles heated by nuclear fusion, pushes back. This balance is called hydrostatic equilibrium. It is not perfectly still, but it is stable enough for the Sun to shine for billions of years. The structure of atoms matters here because stars are made from matter that follows quantum rules. In the Sun's core, hydrogen nuclei fuse into helium through nuclear reactions, releasing energy. The electrons and nuclei form a hot plasma rather than neutral atoms in the ordinary sense. But the basic identities of particles, the electromagnetic force, quantum states, and nuclear binding all remain essential. In more extreme stars, quantum rules become even more dramatic. When a star like the Sun eventually exhausts the nuclear fuel in its core, it may leave behind a white dwarf. A white dwarf is the dense remnant of a star, roughly comparable in mass to the Sun but compressed into a size similar to Earth. Ordinary atoms cannot remain arranged in the usual gentle way under those conditions. Matter is squeezed until electrons are forced into a highly compressed quantum state. Here, the Pauli exclusion principle becomes vital again. Electrons are fermions, and identical fermions cannot all occupy the same complete quantum state. When matter is compressed in a white dwarf, electrons are forced into higher and higher momentum states because the lower available states are already filled. This creates electron degeneracy pressure. It is not ordinary heat pressure in the usual sense. It comes from the quantum refusal of electrons to be packed into identical states. Electron degeneracy pressure can hold up a white dwarf against gravity. This means a dead star can avoid further collapse, not because it is still burning fuel like the Sun, but because quantum mechanics itself pushes back. Subrahmanyan Chandrasekhar showed that this support has a limit. The Chandrasekhar limit is the maximum mass a white dwarf can have before electron degeneracy pressure can no longer support it against gravity. This limit is about 1.4 times the mass of the Sun. Above that, the white dwarf cannot remain stable in the same way. Gravity becomes too strong, and the star must change, collapse, or explode depending on its circumstances. This is a stunning extension of the same story. The Pauli exclusion principle helps explain why electrons fill atomic shells. It helps explain why matter takes up space, and in white dwarfs, it helps hold up an entire stellar remnant. Under even more extreme conditions, a neutron star can form. This can happen after the core of a massive star collapses during a supernova. In a neutron star, matter is compressed so violently that ordinary atoms are destroyed. Protons and electrons are driven together, forming neutrons through processes involving the weak nuclear force. The result is an object with more mass than the Sun packed into a sphere only tens of kilometers across. A neutron star is not made of ordinary atoms in the familiar sense. There are no peaceful electron shells, no normal chemistry, and no cozy molecular arrangements. This is matter pushed far beyond the usual atomic world, but quantum principles still matter. Neutrons are also fermions. Like electrons, they obey the Pauli exclusion principle. When neutrons are compressed into an incredibly dense state, neutron degeneracy pressure helps resist further collapse. The strong nuclear force also becomes deeply important. Together, these effects can support a neutron star against gravity, at least up to another limit. Beyond that, gravity may win completely, and the object can collapse into a black hole. So the rules that keep matter stable are not weak little details. They're cosmic. They shape the lives and deaths of stars. They decide whether a stellar core becomes a white dwarf, a neutron star, or something even more extreme. They turn quantum mechanics from a theory of tiny particles into a force in the architecture of the universe. These extreme objects are not examples of atoms remaining intact in the normal way. In white dwarfs, atoms are compressed and stripped into dense matter. In neutron stars, ordinary atomic structure is gone altogether, but the deeper theme remains. Quantum rules prevent simple collapse, at least until gravity becomes overwhelming. The same principles that stop electrons from all sinking into the lowest state near a nucleus can also stop a star's remains from falling inward without resistance. Atoms do not fall apart because quantum mechanics gives matter structure, and in the densest stars that structure becomes strong enough to hold back gravity itself. It is one thing to say that atoms are stable. It is another thing to show it. After all, atoms are far too small to see directly with ordinary eyes. We cannot pick up a hydrogen atom, turn it over thoughtfully, and check whether the electron is behaving itself. The atomic world has to be known through evidence: light, scattering, measurement, instruments, and patterns that repeat with extraordinary reliability. Fortunately, atoms leave clues everywhere. One of the most important clues is spectroscopy. Spectroscopy is the study of how matter emits and absorbs light. When atoms are excited, they do not usually emit light in every possible colour. Instead, they emit light at specific frequencies, producing sharp spectral lines. These lines reveal that atoms have discrete energy levels. This is exactly what quantum mechanics predicts. If electrons in atoms could have any energy at all, then atomic light would be much more continuous and blurred. But because electrons occupy allowed quantum states, atoms absorb and emit light only when electrons move between those states. The energy of the light corresponds to the difference between the two levels. Hydrogen is the classic case. Its spectral lines are so regular that they became one of the great puzzles leading toward quantum theory. The patterns associated with Johann Balmer's formula, and later with the broader Rydberg formula, showed that hydrogen had a hidden numerical order. Bohr's model explained part of that order. Schrödinger's wave mechanics later explained it more deeply. Spectroscopy is not limited to laboratory flames and glowing gas tubes. It is one of the main tools of astronomy. When light from stars passes through cooler gas, certain frequencies are absorbed. When hot gas in nebulae shines, it emits characteristic lines. By reading these patterns, astronomers can identify hydrogen, helium, oxygen, iron, calcium, sodium, and many other elements across space. The same atomic rules that operate in a laboratory on Earth operate in the atmospheres of stars and the clouds between them. That is a powerful kind of evidence. Atoms are not stable only when gently supervised by scientists in clean rooms. They behave consistently across galaxies. Another major line of evidence came from electron diffraction. Clinton Davison and Lester Germer showed that electrons scattered from a crystal could produce diffraction patterns, confirming that electrons have wave-like properties. Later experiments continued to demonstrate wave behavior in matter, supporting the idea that electrons in atoms are described by quantum states rather than classical paths. Modern instruments allow matter to be examined with astonishing precision. Electron microscopes use beams of electrons to probe structures much smaller than visible light could resolve. Because electrons have wave-like properties with very short wavelengths when accelerated, they can reveal fine details of cells, crystals, materials, and nanoscale structures. They do not let us watch electrons orbiting nuclei like tiny moons, because that picture is not correct, but they do show how atomic and molecular structures shape the visible forms of matter. Scanning tunneling microscopes go even further into the atomic landscape. Developed by Gerd Binnig and Heinrich Rohrer, the scanning tunneling microscope uses the quantum effect known as tunneling to map surfaces at the scale of individual atoms. A sharp conducting tip is brought extremely close to a surface, and a tiny tunneling current depends sensitively on the distance between the tip and the atoms below. By measuring that current, scientists can build images of atomic arrangements on surfaces. This does not mean atoms are being photographed like little marbles. It means their electronic structure is being probed through quantum behavior. Still, the result is wonderfully direct. Matter has atomic structure, and that structure is stable enough to be measured, mapped, and manipulated. Atomic clocks provide another extraordinary confirmation. An atomic clock works by using a stable, repeatable transition between energy states in atoms. Cesium atomic clocks, for example, are based on a precise transition in cesium atoms. The modern definition of the second is tied to the frequency of radiation, associated with a particular transition in cesium-133. That is not just a technical detail, it means timekeeping itself depends on the reliability of atomic structure. Institutions such as the National Institute of Standards and Technology have played major roles in developing and refining atomic clocks. Optical atomic clocks, which use transitions at much higher frequencies than microwave cesium clocks, have become even more precise. They are so sensitive that they can measure differences in gravitational time dilation over height changes small enough to matter in a laboratory. That is, atoms, quantum mechanics, and Einstein's relativity all quietly agreeing to make clocks almost absurdly good. Precision measurements of hydrogen remain central as well. Hydrogen is simple enough to calculate in great detail and precise enough to test the foundations of quantum mechanics and quantum electrodynamics. Tiny shifts in hydrogen's energy levels, including the Lamb shift, show that even subtle effects predicted by modern theory can be measured. Large research organisations and laboratories contribute to this wider picture. The European Organisation for Nuclear Research, known as CERN, probes the deeper structure of matter through particle physics. Major university laboratories investigate atomic physics, condensed matter physics, quantum optics, and precision metrology. Across these fields, the same message appears in different forms. Atoms have stable structures governed by quantum laws. The stability of atoms is therefore not something we assume only because tables, rocks, and people seem to exist. It is tested through spectroscopy, electron diffraction, atomic clocks, scanning tunneling microscopes, electron microscopes, chemical measurements, particle experiments, astrophysical observations, and precision measurements of simple atoms. Every line in a spectrum, every reliable atomic clock transition, every mapped surface atom, every molecule with a predictable shape, and every star whose light carries elemental fingerprints adds to the evidence. Atoms do not merely appear stable from far away. They are stable in ways that can be measured, repeated, and understood. And the quantum explanation has survived because nature keeps giving the same answer back. So why don't atoms fall apart? The deepest answer is that atoms are not tiny classical machines. They are quantum systems. Their electrons are not little charged planets moving along neat circular paths, gradually radiating energy until they crash into the nucleus. They are quantum objects described by wave functions, occupying stable states that do not behave like classical orbits. That is the shift that changes everything. In the older picture, the atom looked impossible. A negatively charged electron was attracted to a positively charged nucleus. If that electron moved around the nucleus in a curved path, classical electromagnetism said it should radiate energy. As it lost energy, it should move inward. As it moved inward, it should radiate more. Very quickly, the atom should collapse. But real atoms do not behave this way. The electron in an atom occupies allowed quantum states. These states have specific energies and structures. The electron cannot simply slide through every possible energy on a smooth path toward the nucleus. Bound electrons have quantized energy levels. They can absorb or emit light when moving between allowed states, but they do not continuously leak energy while sitting in a stable state. This is why quantized energy matters. It turns the atom from a collapsing classical system into a structured quantum system. There is a lowest allowed energy state, called the ground state. The ground state is not nothing. It is not the electron sitting motionless inside the nucleus. It is a stable wave function pattern around the nucleus, with energy, shape, and spatial spread. The wave function is central to this answer. It describes the possible states of the electron and lets physicists calculate probabilities, energies, and orbital shapes. Atomic orbitals are not little roads. They are stable probability patterns. Some are spherical, some have lobes, some are more complex, but all of them are quantum arrangements, not miniature tracks drawn through space. The uncertainty principle also helps explain why collapse is not the lowest possible outcome. Werner Heisenberg's uncertainty principle says that an electron cannot have both an exactly defined position and an exactly defined momentum in the classical sense. If the electron was squeezed into an extremely tiny region near the nucleus, its momentum and kinetic energy would become very large. So the atom's lowest energy arrangement is not a perfectly localized electron buried at the center. It is a spread out quantum state. Then comes the Pauli exclusion principle. Wolfgang Pauli's rule says that no two identical fermions can occupy the same complete quantum state. Electrons are fermions, so in larger atoms they cannot all pile into the lowest state. This gives atoms their shells and subshells. It helps explain the periodic table, chemical families, and the structure of ordinary matter. It is also one of the reasons matter resists compression instead of collapsing into a dense, featureless blur. The electromagnetic interaction remains essential as well. The negative electron is attracted to the positive nucleus. Outer electrons repel the electrons of neighbouring atoms. This attraction and repulsion, combined with quantum rules, gives atoms size, allows chemical bonds, and makes solid matter feel solid. A table holds up a hand not because atoms are tiny hard marbles, but because their electron structures resist being pushed through one another, and the nucleus has its own stability. Protons repel one another electrically, but the strong nuclear force binds protons and neutrons together over the tiny distances inside the nucleus. Neutrons help stabilize many nuclei, while nuclear binding energy determines which arrangements are favored. Some nuclei are radioactive and transform over time, but many are stable because their nuclear structure has no lower energy transformation available under ordinary conditions. So there is no single magic phrase that explains atomic stability on its own. The full answer is woven from quantist energy levels, wave functions, the uncertainty principle, the Pauli exclusion principle, electron shells, electromagnetic attraction, and repulsion and nuclear binding. Quantum mechanics explains why electrons do not collapse inward. Nuclear physics explains why many nuclei remain bound. Together they explain why atoms can last. This is why matter feels ordinary. not because it is simple, but because its strangeness is dependable. Every breath depends on stable nitrogen and oxygen molecules. Every drop of water depends on stable hydrogen and oxygen atoms forming stable bonds. Every living cell depends on carbon, nitrogen, oxygen, phosphorus, sulfur, and countless molecular structures holding their arrangements long enough for biology to happen. Every planet depends on atoms forming minerals, metals, ice, rock, atmosphere, and ocean. Every star depends on nuclei, electrons, plasma, pressure, fusion, and quantum rules operating under enormous conditions. Even technology depends on this stability. Semiconductors, lasers, atomic clocks, medical scanners, screens, batteries, magnets, and chemical reactions all rely on the fact that atoms have repeatable structures and measurable energy levels. The atom is not a vague idea hidden beneath the world. It is the reason the world has reliable behavior at all. The strange part is that none of this feels strange while we live inside it. Matter holds together quietly. A room does not advertise its quantum foundations. A stone does not announce the Pauli exclusion principle. A glass of water does not pause to explain molecular orbitals before being drunk. The rules operate silently, everywhere, with almost unimaginable consistency. The atom is not a tiny solar system. It is a stable quantum arrangement. At its center is a nucleus held by nuclear forces. Around it are electrons described by wavefunctions, shaped into allowed states, restricted by uncertainty, organized by exclusion, and bound through electromagnetism. It survives not by avoiding the weirdness of quantum physics, but because of it. And that is the deep answer beneath the atom. Matter remains standing because the smallest parts of it are not classical at all. So, why don't atoms fall apart? The clearest answer is that atoms are not held together by the rules of classical physics alone. They are held together by quantum mechanics. Electrons do not behave like tiny charged planets, orbiting a nucleus along neat, fragile paths. They occupy stable, allowed states, shaped by wave functions, energy levels, uncertainty, and the Pauli exclusion principle. And at the center of the atom, protons and neutrons are held together by nuclear forces, especially the strong nuclear force, which binds the nucleus over extremely short distances. The atom survives because its parts are not free to do just anything. That is the quiet secret beneath matter. At the beginning, the problem looked almost obvious. Solid objects feel stable. A table remains a table. A stone keeps its shape. A hand does not pass through a wall, which is generally helpful for both hands and walls. Yet all of these things are made from atoms, and atoms are built from charged particles and empty-seeming space. Once scientists began looking inside matter, stability stopped being obvious. Classical electromagnetism, developed through the work of James Clerk Maxwell, said that accelerating electric charges should radiate electromagnetic energy. That created a terrible problem for the old planetary picture of the atom. If an electron were orbiting a nucleus like a planet around a star, it would be constantly changing direction. That means it would be accelerating. And because the electron is electrically charged, it should radiate energy, lose that energy, spiral inward, and crash into the nucleus. According to that classical picture, atoms should not last. Hydrogen should collapse. Carbon should collapse. Oxygen should collapse. Matter should never settle into the stable forms needed for chemistry, planets, stars, biology, or anything as pleasantly unremarkable as a quiet room at night. But atoms do last. Ernest Rutherford's gold foil experiment, carried out with Hans Geiger and Ernest Marsden at the University of Manchester, revealed that the atom contains a tiny, dense, positively charged nucleus. This replaced J.J. Thomson's earlier plum pudding model and gave physics a far more accurate picture of the atom's structure. But it also made the problem sharper. If the positive charge was concentrated in a nucleus, then the negative electrons outside it seemed even more strongly drawn toward the centre. Niels Bohr offered the first great quantum rescue. In 1913, he proposed that electrons in hydrogen could occupy only certain allowed energy levels. They could emit or absorb light when moving between these levels, but they did not radiate energy continuously while remaining in an allowed state. Bohr's model explained the spectral lines of hydrogen, especially the patterns connected with Johann Balmer's work, and it showed that quantization was essential. But Bohr's model was only the beginning. Louis de Broglie then suggested that matter itself has wave-like properties. Electrons were not merely particles in tiny orbits, they could behave as matter waves. Clinton Davison and Lester Germer later confirmed electron diffraction, showing that electrons really do display wave-like behaviour. This changed the meaning of atomic stability. Electrons could form stable wave patterns around the nucleus, more like standing waves than little beads racing along invisible tracks. Erwin Schrödinger gave this idea its powerful mathematical form through the Schrödinger equation, which describes the behaviour of the wavefunction. The wavefunction is a mathematical description of a quantum system, allowing physicists to calculate possible states, energies, and probabilities. Max Born then gave the wavefunction its probability interpretation. An electron in an atom is not assigned a simple classical path. It is described by a distribution of possible measurement outcomes. Atomic orbitals come from this picture. They are not circular roads. They are stable wavefunction patterns around the nucleus. Some are spherical, some have lobes, some are more complex. But all of them represent allowed quantum states, not classical tracks. Werner Heisenberg's uncertainty principle added another essential piece. An electron cannot have both an exactly defined position and an exactly defined momentum in the classical sense. If the electron were squeezed into an extremely tiny region near the nucleus, its momentum and kinetic energy would become very large. So the lowest energy state of hydrogen is not the electron sitting motionless inside the nucleus. It is a spread-out ground state, stable, structured, and quantum. The ground state matters because it stops the endless fall. The electron cannot keep losing energy forever, because there is no lower allowed atomic state for it to occupy. The atom's stability is not emptiness or stillness. It is motion and structure arranged into precise allowed patterns. Wolfgang Pauli's exclusion principle then explains why larger atoms have architecture. Electrons are fermions, and no two identical electrons in an atom can occupy the same complete quantum state. Enrico Fermi and Paul Dirac developed the statistics that describe fermions more broadly. Because of these rules, electrons fill shells and subshells instead of all collapsing into the lowest available state. Those shells explain the periodic table. Dmitri Mendeleev saw the repeating patterns of the elements before quantum mechanics could explain them. Quantum theory later revealed that the outer electron arrangements of atoms give rise to chemical families such as noble gases, alkali metals, and halogens. From electron shells come chemical bonds, molecular shapes, and the structure of ordinary substances. Chemical bonding extends atomic stability into the larger world. Gilbert N. Lewis helped clarify the role of valence electrons, while Linus Pauling connected chemical bonds to quantum mechanics. Ionic bonding, covalent bonding, and molecular orbitals all depend on stable electron arrangements. Water, carbon dioxide, proteins, deoxyribonucleic acid, minerals, and the chemistry of life all rely on atoms remaining stable enough to combine. The nucleus has its own stability story. Protons repel one another electrically, but the strong nuclear force binds protons and neutrons together over tiny nuclear distances. James Chadwick's discovery of the neutron helped explain nuclear structure, while Hideki Yukawa's work helped develop early theories of nuclear forces. Stable nuclei have favourable nuclear binding energy, meaning their bound arrangements are lower in energy than separated particles. Some atoms do transform. Henri Becquerel, Marie Curie, and Pierre Curie helped reveal radioactivity, showing that certain unstable nuclei undergo alpha decay, beta decay, or gamma emission. But radioactivity does not mean atoms generally fall apart. It means some nuclear arrangements are unstable and can move toward more favourable states. Many nuclei, including common forms of hydrogen, carbon, nitrogen, oxygen, and iron, remain stable across immense spans of time. Modern quantum electrodynamics deepens the story further. Richard Feynman, Julian Schwinger, Shinichiro Tomonaga, and Freeman Dyson helped build the quantum field theory of electromagnetism, describing electrons, photons, and their interactions with extraordinary precision. The Lamb shift, measured by Willis Lamb and Robert Rutherford, showed that tiny shifts in hydrogen's energy levels could be explained by subtle quantum field effects. Even the electron's magnetic behavior can be predicted with astonishing accuracy. And the same rules do not stop at atoms. In stars, planets, gas clouds, white dwarfs, and neutron stars, quantum structure shapes the behavior of matter. Subramanian Chandrasekhar showed that electron degeneracy pressure can support white dwarfs up to the Chandrasekhar limit. In neutron stars, neutron degeneracy pressure and nuclear forces resist collapse under conditions far beyond ordinary matter. These are extreme cases, but they show how deeply quantum rules are woven into the universe. So the contrast is clear. Classical physics predicted collapse. Quantum mechanics revealed stable ground states. The atom is not stable because nothing is happening inside it. Quite the opposite. Electrons exist in wave-like states. Nuclei are bound by powerful forces. Fields interact. Energy levels define transitions. Particles obey exclusion rules. Light is emitted and absorbed in precise amounts. Matter is alive with structure, but that structure is disciplined. It follows allowed patterns. That is why the universe has long-lasting form instead of dissolving into electromagnetic chaos. Every table, star, leaf, hand, stone, breath, ocean, cloud, and living cell depends on this quiet quantum achievement. The rules are far too small to see directly, yet strong enough to make a world. They hold electrons away from collapse. They bind nuclei together. They give atoms size, chemistry, stability, and identity. Matter seems ordinary because it is so reliable. But beneath that reliability is something extraordinary. The atom does not fall apart because nature is not classical at its deepest levels. It is quantum. And in those quantum rules, the universe found a way to build things that last.